Whether astronomers or ordinary people, before the 20th century, everyone believed that the size of the universe was fixed and that it was overall in a stable state. After 1915, with the advent of general relativity, people gradually gained a completely new understanding of the space within our universe. By solving the field equations, Einstein surprisingly discovered that our universe seemed to be undergoing a process of dynamic change. This result left him deeply unsettled, prompting Einstein to add a parameter to the equations in an attempt to force the universe back to a static state. Later, this manually added cosmic constant became known to have significant issues. Firstly, even with this constant, the theory's depiction of a static universe was still inherently unstable. Secondly, Hubble's subsequent observations confirmed that the universe was indeed expanding. In 1922, Soviet mathematician and cosmologist Alexander Friedmann found a significant solution to the gravitational field equations, which later became known as the FLRW metric. Building upon the cosmological principle of isotropy, Friedmann formulated a set of equations for an expanding universe model, known as the Friedmann equations. Through these equations, we can understand how the universe evolves over time. Regardless of the shape or curvature of our universe, it undergoes an expanding phase for a certain period, but the rate of expansion gradually slows down. This makes sense, considering that ordinary matter in the universe attracts each other due to gravity. Although the initial Big Bang might have blown them apart, over time, this tendency should gradually diminish. However, these were mere theoretical speculations. Was there any evidence? Well, this is where Hubble comes in. In 1929, Hubble observed a type of special star called a Cepheid variable. After measuring several galaxies beyond our Milky Way, he discovered that the farther away these galaxies were, the faster they were moving away from us. Moreover, there was a clear proportional relationship between distance and speed, which became known as the Hubble's law. The decisive constant in Hubble's law was subsequently named the Hubble constant. Speaking of the Hubble constant, it's important to note that this constant only means it's fixed for all galaxies at this moment in the universe, and it's not necessarily permanently unchanging. Even now, different methods of measurement yield slightly different values for the Hubble constant, with some differences even quite significant. Hence, precise measurement of the Hubble constant and understanding the reasons for these discrepancies are current directions in astronomy. Returning to the story, while Hubble observed galaxies moving away, it was Edwin Hubble who connected this phenomenon with the expansion of the universe. However, the idea of the universe expanding was hard to accept, especially for Einstein. He struggled to believe that the size of the universe could actually change. To confirm Hubble's observations, Einstein visited the Mount Wilson Observatory and verified the results firsthand. Faced with the undeniable truth, Einstein regretted adding the cosmological constant, considering it the greatest blunder of his life. From that point on, the fact of cosmic expansion gradually gained acceptance, aligning with the description from Friedmann's equations. Although our universe is expanding today, it's doing so at a decelerating rate. As time goes on, the universe will eventually transition from expansion to contraction, much like a deflating balloon. This view persisted for several decades, including when Stephen Hawking wrote A Brief History of Time, describing the same idea. However, this perspective underwent a fundamental shift in 1998, just as we were entering the 21st century. A team studying high redshift supernovae discovered, from their observations of type Ia supernovae, that our universe was not decelerating but actually accelerating in its expansion. This result was confirmed by another team the following year and earned the 2011 Nobel Prize in Physics. To account for this acceleration, a substance with negative pressure needed to be introduced into the equation, and its quantity had to be far greater than that of ordinary positive pressure matter, even greater than the enigmatic dark matter, which also exerts gravitational effects. What is this substance with negative pressure? Given our limited understanding, it was dubbed dark energy. So far, dark energy exists both theoretically and with corresponding observational evidence. Regarding the supernova evidence for dark energy, there were questions raised by a paper from Yonsei University, South Korea in 2020, suggesting that the luminosity of Type Ia supernovae, once considered standard candles, might not actually be standard. This might necessitate considering their stellar populations, potentially impacting the theory of dark energy. Dark energy as a leading hypothesis is supported by more than just the supernova evidence. Observations of the cosmic microwave background, for instance, also offer compelling support. Using the cosmic microwave background, we can calculate that the overall matter content in our nearly flat universe should be close to or equal the critical density. However, all astronomical observations to date, both visible ordinary matter and the unseen but gravitationally effective dark matter, add up to only about 30% of the critical density. Hence, the remaining portion can be considered even darker than dark matter, aligning perfectly with the concept of expanding universe driven by dark energy. Moreover, there are other lines of evidence, such as baryon acoustic oscillations. In sum, from the multitude of existing evidence, there indeed seems to be something like dark energy in our universe. But what is it? Beyond mathematical explanations like the gravitational field equations, the quantum field theory's prediction of vacuum fluctuations can be interpreted as a form of dark energy. These quantum fluctuations indeed represent a kind of energy seemingly created out of nothing, and they are uniform in spatial distribution. Dark energy's distribution in the universe is also remarkably uniform, increasing only with expanding space. This explains why the distances of galaxies from us and their recession speeds are proportional. However, even this theory encounters a problem. It predicts a dark energy density that is 120 orders of magnitude larger than what is observed. Although this can be mitigated through supersymmetry theory, confidence in supersymmetry has waned in light of contemporary accelerator experiments. The Fermi National Accelerator Laboratory's discovery of the W boson mass deviating severely from particle standard model predictions, with a confidence level of 7 sigma, adds skepticism to the theory. If this result can eliminate potential errors and is confirmed by other colliders like the LHC, there might still be hope for supersymmetry. Of course, alternative explanations for dark energy have been proposed, such as introducing a scalar field known as the fifth element. Yet, each interpretation faces various challenges. Beyond this, the European Space Agency's Euclid mission, set to dominate in the early 21st century, aims to precisely measure the universe's accelerated expansion through various methods to gain deeper insights into the nature of dark energy and dark matter.